This is section 7.5, work. Now you may have been introduced to the concept of work in a physics setting. And as we do with a lot of problems in physics and math, as we simplify things. So we assume in physics, at least in beginning physics, that the force that you apply to an object is constant. And in that case, work is defined to be the amount of the force times the distance. Work equals force times distance. And if you look at the next page in the notes, there are 4 different fundamental types of forces: gravitational, electromagnetic, strong nuclear, and weak nuclear. A force can be thought of as a push or a pull. A force changes the state of rest or state of motion of a body. For gravitational forces on Earth, it's common to use units of measure corresponding to the weight of the object. So one of the units of force you'll see is pounds. For example, example 1, this is a physics type question. Determine the work done in lifting a 50-pound object. So that means that our force is 50 pounds. And we're supposed to lift that 50-pound object 4 feet. And so our distance is 4 feet. So by using substitution, we can find that the work will be 50 times 4, which is 200. And the units for this answer for work is in something called foot-pounds. Foot-pounds. Okay. So that's just a simple physics level question, and it's very easy and not so hard to understand. Using U.S. measurement systems, we'll see work like this example expressed in foot-pounds, or perhaps in inch-pounds or in foot-tons. In the international system of units, the basic unit of force is the Newton, which you may have encountered this in a physics setting. A Newton is the force required to produce an acceleration of 1 meter per second on a mass of 1 kilogram. In this system, work is typically expressed in Newton meters, also known as joules. In another system, the centimeter gram second system, the basic unit of force is the dyne, the force required to produce an acceleration of 1 centimeter per second on a mass of 1 gram. In this system, work is typically expressed in dyne centimeters, also called ergs, or converted back to joules. In the next table, you'll see some of the conversions and different units of measurement for different things. And you will not be converting between these units. So I wouldn't worry about that too much, but just familiarize yourself with the types of units that you may encounter. Now, the thing that makes this a calculus problem for us is if we have, for example, a variable force being applied to an object. I think, for example, like if you were lifting a bag of oats, but there was a hole in that. And so as you lifted it up, the oats were falling out. And so the force was changing. It was decreasing as your oats leaked out of the bag. And so that would be a variable force. Another example of that is the force required to compress a spring will increase as the spring is compressed. So let's look at a partition for a very small partition that divides the distance you're going from x equals A to x equal to B into small intervals. We can assume on that small interval that for that amount of distance that we're moving, the force won't change by much. And so this is that small unit where we're going to use this pre-calculus idea, this one that I've written, work is equal to force times distance. That's our basic idea. And for small increments of change, we'll be able to say that we do have a constant force and distance as an approximation of the actual work done on that small increment of time. And so, again, we'll add up infinitely many of those and get to an integral. And you can read through how that's developed, and it's a good exercise in seeing how this is another example of what we've been talking about. But as it turns out, the force function that we will have that's changing will be f of x, and work will therefore be the sum of infinitely many little force, which will be f of x, times distance moved, delta x, which will be dx in this integral. And so that's our formula for work. And you'll need to know this, commit it to memory. Okay, so if you want to read through that explanation and see how that idea is developed, it's very similar to some of the other developments that we've gone through. So, there are several laws of physics written by some very famous physicists and scientists that we may very well end up using in some of our problems. The one I really want you to know is Hooke's law, so pay attention to that one in particular. It is the one that you'll probably encounter the most in this course. So let's look at that one. Hooke's law is the force F required to compress or stretch a spring within its elastic limits is proportional to the distance d that the spring is compressed or stretched from its original length. Notice that's underlined. That's probably the hardest part for most students to get right. The measurement is how far it is from its original length. That is, if we're not touching the spring, if we're just lying on a table, how long would it be? That's its natural length. And any distance you move is from that length, not measuring how long the spring is itself, but how far it's been moved from that natural length. So, at any rate, Hooke's law says that because you have that proportionality, that means that there's going to be some k times the distance that gives you that force. And k depends on the kind of spring you have. You can imagine that a little bitty slinky, I don't know if you played with those toys, but that's a very loose spring, easy to manipulate, versus a spring that holds the garage door in place. Very heavy spring with a lot of force in it. You don't want to be near one of those if it breaks. It really can be kind of destructive. So we'll come back to that again. So this is Hooke's law, where that force function will be found for a particular spring using this equation. The other two, if you encounter them in homework or a quiz or something, you're welcome to look up these formulas as needed. I do not want you to memorize them. So there's Newton's law of universal gravitation. And then on the next page, Coulomb's law, which is dealing with the force between two charges in a vacuum. And as I said, those G, M1, and M2 would be constants. And d would be the distance it's changing, so that would be a variable, and f would be a variable force. Likewise, k, q1, and q2 would be constants for a particular problem. All right, so let's do a Hooke's law problem as an example and see where that gets us. So we're told that a force of 30 newtons, so we have a force of 30 newtons, compresses a spring 0.3 meters from its natural length of 1.5 meters. Okay, so the distance that this force causes the spring to be from its natural length is 0.3. So notice I'm not using the 1.5, except for perhaps as a comparison. Like if it said that it would compresses it to be 1.2 meters long, then what we would be looking for is how far is that from the natural length of 1.5, and that's how we could get the 0.3. Okay, so what that piece of information is needed for is for us to be able to substitute into Hooke's law. For f, we'll put in 30. K is unknown, and the distance is 0.3. And then solving for k makes this the proportionality constant for this particular problem. And so we get k equals 100, which implies for the rest of this problem, the force, and I'm going to use x as my variable, is going to be 100 times x, where x is the distance from the natural length. That we might move the spring. Okay? So then the question is, find the work done in compressing the spring an additional 0.3 meters. And so the work done is going to be a definite integral of our force function 100x dx. Okay. Now the hardest part of this problem is not finding k or setting up f of x, but it's in determining the values for the definite integral lower bound and upper bound. So in getting it to be 30, we've already moved it 0.3 meters. So it's already 0.3 meters away from its natural length. And that's the starting point that we're talking about, is at 0.3 away. And then to compress it an additional 0.3, where will it be then? Well, if it's already moved 0.3 plus 0.3, that's going to put it at 0.6. So we're moving it from 0.3 meters from its natural length to 0.6 meters from its natural length. And of course, this one is really easy. It's a very simple linear function, and its antiderivative is super easy, and I'm sure you can do it. So I'm not going to go through the process there. This is one that you can practice if you'd like. And you get 13.5 Newton meters. Or if you prefer, you can say 13.5 joules. You don't need to answer both of those. Either one or the other is sufficient. So if you want to write joules, that's fine, of course. But it's I'll probably think Newton meters because of the standard uses foot pounds, and so I'm used to that two name unit. Okay. Please notice that we did not start this integral at 0. It was already 0.3 away, and it was moving another 0.3 away. So be very careful. So let's do another example of this. We're going to use the exact same spring, so the force will still be 100x. And I want to ask this question: how much work is required to compress this same spring from a length of 1.4 meters to a length of 0.5 meters. Okay, so the integral itself is going to look the same. The only thing that's going to change here are the bounds. So we're still using the same force, 100x, and work will be the integral of 100x dx from a to b. The question here is, what's a, what's b? So if we're at 1.4, how far are we away from the natural length of 1.5? Well, we're only 0.1 away. So that's 0.1 is where we're going to start at 1.4, which is 0.1 away from 1.5. And then we're going to compress it until we're at 0.5. And how far is 0.5 from the natural length of 1.5? Well, that's 1 away. And so those are the bounds of this integral. As I said earlier, that is probably the most challenging part of these questions, is getting those bounds correct. And it all is tied up with the correct definition of x is how far is the spring from its natural length. Okay, so when we skipped over the development a little bit of how we got this formula to work way back before the formulas and all that were given for the physics, Hooke's law and Coulomb's law and all that. And what we were working with at that time was, and like I said, I kind of skipped over this, is that our change in work, our delta W, was force times an incremental change in x, the distance. And so we considered, for that small change in distance, we could assume that the force would be relatively constant. And so we could treat it as a constant over that small delta x and get the amount of work that's done as if that F were constant. For a small delta x, we can make that assumption. Another way that we can restate this is, instead of having an incremental distance, we can have a force increment, small change in force, times the distance moving. It's being moved. And this is a particularly good approach, the second one, if the problem we're dealing with involves the movement of non-rigid substances, such as fluids and chains. So let's do example 4 to see if we can kind of understand what's going on here with this alternate approach. So we have a spherical tank of radius 8 feet. That's half full of oil that weighs 50 pounds per cubic foot. Find the work required to pump all of the oil out through a hole in the bottom of the tank. So, in order to get this to make sense to me, I'm going to introduce a coordinate system. And I know that I'm only using 2 of the variables x, y. So what we're going to be seeing when I draw this sphere is a cross-section of it. So this is like the sphere as seen from the side. Now I could have put the center of the sphere at the origin, but actually that would have made this a little bit harder to work with. So pretend like that's a sphere. And what are the coordinates of this point right here, if the sphere is resting at the origin out on the ground? Well, I hope you said 0, 8 and not 0, 4, because remember, the radius is 8, not the diameter. And so the point at the top, of course, is at a level of 16. Okay, so we have oil in this, and it'll look something like this at the top of the oil. So it's half full. And what we're going to do is we're going to have a slice of water, if you will, that we're going to cut out of here, a representational slice of water, just somewhere random. And we're going to make an assumption that that's cylindrical in shape. It doesn't exactly match that is going to be an approximator for us, is that cylindrical slab of oil. Okay, so the height of that is delta y. Okay, and the radius there, the radius right there, is, since that's a generic place, we're going to call that the distance from the y-axis to the edge of the tank is a value of x. And so the radius is x. All right, so we have that that one slab of oil, if you will. If I say water accidentally, that's what I always say accidentally. It's oil, though. We're supposed to move this representative slice or cylinder of oil. See, I told you I'd do that. We need to move it from its present location to the top of the tank. And so that's the distance we have to move that. And of course, the distance from the x-axis to the top of the tank is always 16. And if this ordered pair right there, where the cylinder of water is touching the edge of the tank, the coordinates of that point are, let me write it out here, x, which is where we got the radius as x from, comma y. And of course, the distance from the y-axis to that level is our value of y. And so the distance we're going to be moving the bit of material from the oil, from where it is to the top of the tank, that's a value of 16 minus y. That's how far we're moving it, 16 minus y. Okay, so let's see what we can do here. So the incremental force that we're dealing with here is the weight of that one cylinder of water. Now, to get that weight, they did tell us something about that it weighs 50 pounds per cubic foot. So I'm going to write that down, 50 pounds per cubic foot. But that's not a unit of weight. That's actually density. And so think about the units there. What would I need to multiply pounds per cubic foot by to get pounds? What would I have to multiply by? Well, I'd have to multiply by cubic feet, right? So the cubic feet would cancel, leaving pounds. So what is measured in cubic feet? Well, that's the volume. And so what we're going to need to do is to find that volume of that cylinder of water. And of course, we know the formula for the volume of a cylinder is pi times r squared, and we already identified the radius as x. So pi r squared. Then the height of that cylinder is delta y. Okay? So that means that, going back to our weight, we're going to have 50, the density, multiplied by pi times x squared times delta y. Now you may have noticed a little hole in this idea, is that if I'm using delta y, that means my integral is going to have a dy in it, and I can only use a y variable in that integral. I cannot use x. I can't have a mixture of variables. So I'm going to have to get rid of that x. And so let's go back to my picture for a second. The center of that circle, and of course this is just a cross section of the tank, but the center of that circle, which is the center of the sphere, is at 0, 8, because we put the bottom of it at 0, 0. And so what is the equation of a circle? Well, of course, it's x minus the x-coordinate of the center squared plus y minus the y-coordinate of the center squared, where the center is called hk, and that sum of two squares is equal to the square of the radius. And so that means that since the center of the circle is 0, 8, this will be x minus 0 squared plus y minus 8 squared, and the radius, of course, is 8. And so this equation simplifies to be x squared plus y minus 8 squared equals 64. And that means that x squared is equal to 64 minus, let's go ahead and do that squaring, y squared minus 16y plus 64. And then doing the subtraction by carefully distributing that subtraction over the parentheses, that's going to leave us with negative y squared plus 16y. Okay, so that's what x squared is. So I'm going to come back over here to where we were working, that delta f, and that's going to be 50 pi, and then we can take out the x squared and put in its place 16y minus y squared delta y. Okay, so that's the incremental force. Now, that means that our delta W, as you saw in the second option up there above, you can just barely see it right now, is going to be delta F. So that's our expression we just found. Let me copy that down. Okay. And that's to be multiplied by our distance that we're moving it. I know I wrote x up there, but that was to represent distance of movement. So, and how far are we moving this thing? Well, we already established that we're moving it 16 minus y units from its current location to the top of the tank. And so our integral for this will be, if we add up infinitely many of those disks of oil that are being moved to the top of the tank, the work that we do will be the integral of that expression, 50 pi times 16y minus y squared times 16 minus y, and then the delta y becomes dy. All right, now what we have to worry about is, what are the bounds of this integral? What y values are we using? So look at where the oil is right now in its original position. What are the y values of where there is oil? Well, it starts at the bottom at where y is 0 and goes up to the point, because it's half full, to 8. If the thing had been full, we would have gone 0 to 16. If it had been 3/4 full, we would have gone 0 to 12. Okay, so that's the integral. I'll leave that to you as an exercise to practice for doing some calculus 1 level integration, which involves simplifying that product, pull the 50 pi out, do the product of those two binomials, giving you a polynomial to integrate, and then evaluate that. And you should get something that is about, so I should have written approximately, 589.782. So I'd like for you to check yourself on that. And the units are in foot pounds. Foot-pounds. Okay. Let's see what's next here. So that is the end of this section. I will see you in class.